Okay, so I'm gonna show some of what I've been working on. Give a little demo. So this is what you're looking at right now is the simulator for my project. The idea is I want to navigate through a flooded environment. So what I've done is create this framework that allows me to do that via these aerial images. So right now I'm showing down in the bottom corner here. This shows like the predefined area that I made in Unity. So I'm using this Mapbox tool, which kind of automatically generates this environment. And I've simulated this sort of flooded area where I've added in water, which is realistic to how it would look in the real world. So what I'm going to do is I've written some scripts in Python, Unity. I'm going to basically simulate flying a UAV in a pattern over this area. And as it flies over the area, it stitches together these images that it takes of that environment that I've created. And it also classifies the images. So you can see here, it's doing that. So it's creating a mosaic. So the simulator basically acts like the UAV, and then it sends these images over TCP/IP to a Python process that's stitching them together. So this kind of simulates how it would work. In the real world, you'd have a UAV flying over this affected area and then streaming these images back to this process that does the stitching. Additionally, as these images are coming in from the simulator, these images here, they're classified, and then based on the transform found to stitch these images together, the classified images are also stitched together, as you can see here. So based on the classification, basically there's a weighting assigned to each of the pixels that says like how difficult it would be to navigate through the area. So this is a heat map. It's obviously like traveling through the flooded area, it's very difficult. So you see there's a high cost associated with that. Whereas traveling along the roads, you can see this darker color, this black here. And then, there's kind of a background class colored sort of in the middle. So these weightings are relative. It's easiest to travel along the roads, whereas, traveling through the background, which might be, a field or trees, is a little more difficult. And then traveling through these obstacles is very challenging. I'm using super points and super glue to stitch everything together. So you can see that process kind of happening now. And then I trained a deep lab model to do the classifications. And once this is done, it will pop up a new view that kind of prompts the user to find a goal location for this overall navigation problem. So now that it's done, it's popped up this view, which basically is just a prompt for the user to define some location to travel to. So I've been using this like tennis court area as a test. So when I define that, you can see it will start this wavefront algorithm. So the idea is basically, this is a dynamic programming solution based on the first cost map that I showed that was stitched together. This will find the cost basically from every location to the goal. So it starts at the goal and it says, what's the cost of transitioning from, a state directly adjacent to the goal, which in this case could be up, down, left, or right. So maybe the state directly above the goal, what would the cost be to move from the goal to that position? So for example, that could be a cost of 1. And then, from that position, what would the cost be to move to the goal, given the adjacent states? So it sort of starts here and slowly works its way outward. That's why it's got that name, wavefront. And then when everything is done, when it's done running, you can start at any point you want. So I could say, for example, start out here and just follow the gradient of this down, and I'll always reach this endpoint. And you can actually kind of see, the goal point I defined is like this kind of black hole here. And then, the further away you get, things start getting lighter. So you can almost even visually do it. If I started here, I just want to try and follow, look for the darker areas. So just try and go to where it looks darker, which obviously here's the darkest. And if I kind of look at this, maybe it's something like that. It looks kind of darker this way. And then, it's definitely getting darker over here. So I could kind of follow this back down. It's my goal area. So that's how this algorithm works. And you can do that for any location. I could start here and say, okay, I want to move down this way, or here and move there. So it's the idea. So basically, once you're done stitching these together, you run this algorithm, and then that process takes a couple minutes. But once you've done this, you can navigate in real time from anywhere within this area, which will be the next thing that's demonstrated. All right, so now the wavefront algorithm is done. It starts the navigation phase. So this view, you're actually looking at the live view from the simulator. So what's happening right now is the UGV is traveling along the path that is decided by the wavefront algorithm. So this bottom view here is kind of like a first or third person kind of view for the UGV. And then this is the UAV. So this is happening live. This is sort of like the simulation of the world. And then this information, this image captured by the UAV is actually streamed to Python. And I'll show what's happening. So here you've got this is kind of the global panorama that was created. And this actually shows the basically the global objective, which is this path whose goal is to get to that point that I had defined earlier in this tennis court over here. So you can see as the UGV moves around, it continues to be able to kind of plot this path in real time. This view here, this square, is actually the view of the UAV. So this is using template matching to localize the area that the UAV is seeing, and also to localize the ground vehicle. So right now, one of the assumptions I'm making basically is just that the UAV is always kind of directly over the ground vehicle. So basically the localizing this UAV kind of also by extension localizes the UGV. So again, this is using template matching. So you can see here This is actually the image from the original panorama. And then this is the live image that's actually being streamed from the Unity simulator. So in this view, you actually can see the UGV agent following along this road, whereas this view, you don't get that. You just are seeing the original panorama. So it's taking this template image and rastering along the original panorama until it finds basically an area, which in this case is the area inside of this box, that is most similar to the template. And that's done by providing some kind of distance metric. In this case, it's a cross correlation. So you can see how that part of this process works. In order to accomplish this global objective, what's actually happening is it's only really following a very simple like local objective, which is basically given the area inside of this box. Just kind of how can you follow a path that would help you accomplish this global objective. So it's using that generated wavefront map, but it's only using, a local area of it. So you still are doing gradient descent, but you're not actually doing gradient descent all the way to the goal as you are in the global objective. You're just doing gradient descent to the smallest value inside of this whole inside of this sort of image. So, for example, right now we could be maybe a cost of 200 away, and the edge of the image is maybe a cost of 150. So, if I do that gradient descent, it will take me to the edge here, which is, the closest to this, because I've already defined the sort of global objective just by looking at the local area of that generated map, which reflects that global objective. I can actually just send very simple commands to kind of accomplish just a more localized objective, but one that will, if repeatedly done, eventually converge to this global objective. So concretely, what I'm doing is basically just sending a bearing and a force, and the force that I send is actually just a constant, so I'm just having it drive at a constant speed, but I'm sending a bearing which is up, down, left, or right, which are the 4 actions that I defined within kind of this space. So whenever I'm transitioning states, I can only move to adjacent pixels that are up, down, left, or right. So that's actually what Python is sending to Unity, is basically just an up, down. Should I go up, down, left, or right based on the position I'm in right now? And doing that, you can accomplish this objective, which is to get to this end area. So, and you can see it does a pretty good job of following along the roads. The path here that's been plotted does kind of go up, and we go around this watery area, which is the goal again, to kind of come up around this watery area, and then we'll go down this road. So you can kind of see the projected satellite imagery, like we're on a road right here. We're going to come down it, and eventually we'll end up at this tennis court. You see now we're pretty close to the global objective. So once we get there, we'll just terminate. And we ended our global objective. And that's it.